Okay. So the last topic we need to discuss a little bit is related to damages of materials and components which belong to the so-called tribological damages. In this, essentially, we are going to make some considerations about wear in the form of unlubricated wear, that is, for components which are moving one with respect to the other, but without any lubricant. The wear can be essentially divided into three big areas. The first one is called adhesive wear. The second one is called abrasive wear. And the third one is called erosive wear. Just to make a link, wear and corrosion, they can exist together, and they are two synergic phenomena. And in order to avoid corrosion, we have seen that we need to select properly the materials, or in the case in which this is possible, to use surface engineering techniques to modify the surface properties. The same applies to wear. I mean, we need to properly select the bulk material in order to respect the consideration we are going to do now, or we do have also the possibility to modify just the surface properties by using surface engineering techniques. Because also wear, as well as corrosion, it is a phenomena starting from the surface of the components. So what is adhesive wear, and which are the basic mechanisms which underlie this kind of phenomena? We have in mind, as I said before, two sliding surfaces, one against another one, which are loaded by a normal force. So if you remember when we discussed at the beginning about surface engineering technologies, we said that the surfaces of any components, to a different extent that depends on the machining on the components itself, is not a flat surface, but it has, how to say, mountains and valley. That is, it has a specific roughness value, which can be defined according to what we have already said, and which can be characterized, for example, by using a stylus or a laser profilometer. So since we do have roughness on the surface, that is, we do have asperities, when we do have these two sliding surfaces which are pressed one against another one, we need to make a distinction by the apparent contact area and the real contact area. The real contact area is those which is linked to the asperities contact, not to the geometric, let me say, definition which we use, for example, in a case of flat surfaces. And this means that if we have a look for a given applied load to the pressure, that is to the stresses which are existing on two or many of two, obviously, asperities which are in contact, the stresses and pressure can be considerably higher than those which is calculated by using the apparent area, because asperities are very small in extension, and so the normal load is divided by very small areas. And this can result, we do have the possibility to make a modeling of the stress distribution inside the materials corresponding to the asperity contacts. But apart from this here, when we do have these two asperities in contact, what it could happen is that we do have junction formation due to the high pressure values, and then a sort of micro welding between or among the asperities. But since we need to maintain the relative motion between the two surfaces, this means that these micro weldings must be broken. And this explains to us, for example, why we need to consider the friction force, first of all. Secondly, when we do have the necessity to maintain the relative movement to break the micro welding, what is going to happen is that if we think, for example, to two different materials compositions, that the breaking points is not localized where it was localized the original micro welding, but it happens a little bit under the surface of the so-called more weak materials. And this results in a formation of fractures here, where the more weak materials give rise to materials which is going to be transferred to the other counterpart. And so we do have materials consumption, shape of the materials, the weakest one, which is going to be modified. And we do have, for example, weight loss and wear tracks on the weaker materials after the fracture of this micro welding. This is considered for a single point, but you need to consider this kind of phenomena for all the places in which asperities are going to become in contact. As you see, we are not considering, because some engineering cases do involve this phenomena, the use of a lubricant. Now, we need to make two considerations in order to better discuss and understand this adhesive wear called biplasticity. And the final formula, which is important for us, which is the Harshad formula, defined generally like in this red circle. But before discussing this, first question, can we have the formation of micro welding independently from the classes to which the material belong? The answer is no, in the sense that this kind of phenomena with the formation of micro welding is essentially related to metallic-based materials, metallic alloys, having a metallic bond and having the possibility to show plasticity, that is, stresses here which can exceed the yielding strength of the materials. This is not possible for ceramic materials, as well as is not possible for polymeric-based materials when they are thermoset materials or thermoplastic materials working at a temperature value which is lower with respect to the glass transition temperature of the thermoplastic materials itself. So adhesive wear is a tribological phenomena which can alter the surface in the case we do have two metallic, essentially two metallic alloys, two metallic materials which are in contact. This is one consideration, very important. The second consideration is related to the question why the breaking of the micro welding does not occur at the same point where the micro welding has been formed. Well, also for this, we do have an answer, because when we are going to consider the stresses which are present in the asperities in contact, we can exceed the plastic behavior of the materials. That means we can exceed where the micro welding is formed, the yielding strength of the materials itself. And this means that the materials is going locally to undergo plasticity effects. And if we remember, when we do have a plasticity effect, that is, when we exceed the tensile yielding strength of the materials, and we can define now the yielding strength of the materials because we have essentially confined this kind of phenomena to metallic alloys, the materials undergoes to a work hardening phenomena. And so this means that where the yielding strength of the materials has been overcome, the work hardening make these materials more resistant than the rest part of the materials. And so if we need to break, let me say, the welding in order to allow the movement to be still existing, the fracture will be developed on the weaker materials, but under the surface of the materials itself, where work hardening has not experienced because we have not, to a certain depth, overcome the yielding strength of the materials. That is, the fracture will be present in the area in which the materials has not been, let me say, reinforced in terms of resistance by work hardening. So these two phenomena, these two considerations can explain to us because we have also material transfer, that is materials consumption. Now, in order to deal with this kind of wear, I remember adhesive wear, we have a very simple equation which can allow to us to make some consideration and calculation. And this equation is the Harshad wear equations, here reported, where we do have the first term, Q, capital letter, which is going to represent the volume of material which is transferred, or if you want, which is consumed per unit time and per unit length of relative sliding. And this volume per unit time and unit relative length of sliding is equal to a constant K, capital letter, which is called also the Harshad wear coefficient, multiplied by the normal load applied, compressive load, divided by the hardness of the weaker materials, that is, the materials which is going to be consumed. So what we can see from these simple equations, we can see that, and that's obvious, if you reduce the normal applied load, we can have a reduce of the severity of the adhesive wear, as well as if we increase the hardness of the weaker material, we can have a reduction of the material consumption because the yielding strength of the materials is going to be increased as well. And so One guideline which is going to come out by looking to this equation is that we can contrast adhesive wear by increasing the hardness of the surfaces. And we can have different methodologies to increase the hardness of the surfaces, starting from increasing hardness of the metallic alloys through thermal treatments, for example. We will discuss this a little bit, or by using, for example, coatings having an hardness higher than those of the bulk materials. What is very important here to remember is that the harsher wear coefficient, and that's the first time we are going to meet better, this kind of consideration. The harsher wear coefficient is not a property of material alone. I mean, we cannot define, for example, how much is the harsher wear coefficient if the question is how much is the harsher wear coefficient of steel, because the harsher wear coefficient is a characteristic of the coupling of the two materials. So we can define the value of K, the harsher wear coefficient for steel, if we, for example, specify that we are considering steel sliding on copper or steel sliding on titanium, etc., etc. And obviously, if we consider, for example, steel sliding on copper, the K value is different from the case of steel sliding on titanium. So this usually happens in typological problems. Some constant which are present in simple formulation, they are not absolute materials properties, but they are referred, and they must be referred to the coupling we are going to investigate. We said that one possible thing, okay, we have then also wear mechanism maps, which is going to evidence, they are on handbooks, the severity of this kind of problem. Sorry, I missed it. Yeah, okay, one slide should be this one, but in any case, that applies also for abrasive, so we will discuss later. So we said we can increase hardness in order to reduce the severity of adhesive wear, but we can do also another thing. Since the basis of this kind of phenomena is related to the fact that both surfaces, they have a metallic behavior. One example which possible is, for example, to reduce the metallic characteristics of the surface. And this can be obtained as an example, again, by using coatings, for example, non-metallic coatings, which can have an hardness value depending on the material composition, but which can also have the possibility to suppress, if we use ceramic coatings, the metallic behavior of one surfaces. What we have to keep also in mind, looking to the hardness value, which is, if increased, able to reduce the consumption of materials itself, we need to keep in mind that we do have also another possible mechanism of damage due to wear of materials, generally speaking. Again, we are specifying to metals, but this can be applied also to other classes of materials, which is related to the so-called abrasive wear. Which is the difference between abrasive wear and adhesive wear? There is a conceptual difference, even though the basic equation you see here is still the Harshard equations, which must be used, obviously, with a proper K value for the coupling, which is able to give rise to abrasive wear. When we are going to discuss, or when we have in mind adhesive wear, we do have micro welding, as we said before. When we do have instead abrasive wear, the asperities of one materials are not going to weld with the asperities of the other materials, but they are going to enter the surface of the other materials and then make a sort of excavation without any welding. This is abrasive wear, and in order to have this kind of phenomena, we need that one of the two materials must be harder than the other one, just to consider conceptually the single asperities as an indenter that we have, for example, in the micro hardness testing, so able to penetrate on the surface, then to move from the surface on the surface due to the relative motion, and then give rise to excavation phenomena. And there is a condition which is universally accepted, which must be kept in mind in order to understand if abrasive wear can happen or not. And the condition is quite simple. We can have abrasive wear if the hardness of the harder materials is at least 20% higher than the hardness of the materials which will be consumed. So this means that if we make a couple from with two very different materials in terms of hardness, we can have also the rise of abrasive wear damages. And the limit is 20%. And so if we come back to this equation of adhesive wear, what we must pay attention that if we increase the hardness of the weaker materials in order to reduce the volume of materials which is lost per unit time and unit sliding length, the increase in hardness must not lead to a final hardness which is higher than 20% of the other materials. Otherwise, we enter the abrasive wear mechanisms. And here, obviously, the value of K is different because it's different the phenomena which is under the damages of the materials itself. Here you have listed, just to have an idea, hardness value VHN is Vickers hardness number value of some materials, and I just pointed out for you the value of silica, silicon oxide, which is at the maximum 1,200 Vickers, which gave rise to us because this kind of materials is used, for example, for cleaning, polishing by sandpaper that you can find also in normal shops. Because if you look, for example, to the hardest form of steel, that is martensite, you see here we can get values as high as 1,000 Vickers. This means that sandpaper having on the top silicon oxide particles are able to generate abrasive wear of martensite and thus polishing of the martensite itself. But also in the case of, sorry, of abrasive wear, apart from the consideration on the normal load, the general equations say to us that an increase in hardness of the weaker surface is able to reduce the volume, also in this case, of materials, which is consumed for unit time and unit length of sliding. We do have different, as this applies also for adhesive, and it was the slide that I was looking before. We do have different mechanisms in order to increase hardness of, for example, a metallic materials by work hardening, like those we have just discussed, by precipitation hardening, for example, that is without any coatings. Well, what has been found, and you can see here on this picture, is that increasing hardening by work hardening is not so effective in order to reduce the abrasive and then the adhesive wear of the materials itself, as the strains in the process zone are as high or higher than those used in cold working. Precipitation hardening can have beneficial effects, but depends on the precipitate type and their response to high strains, because high strains as well as high stress are localized at the asperities of the material surfaces. And hard, fine precipitates, as in tool steels, have some positive effects. You see here, that's the relative wear resistance with respect to hardness increasing. But the larger particles, as those precipitated, they can be present in aluminum alloys, they do not have essentially effect. And so again, even though the equation say to us that we can act on hardness also for abrasive wear by increasing, without adding nothing on the surface, the hardness of the surface itself, usually in order to prevent abrasive wear damages, the most suitable, the most selected choice is to use a coatings, use a coating in order to protect the component that we want to protect. Having again in mind that we do not need to overcome the 20% indifference in hardness, otherwise we are going to protect the weaker component, but we are going to highly consume the other component, which can become, let me say, weaker in terms of final hardness. There is also some effect in abrasive wear, depending on the shape of the particles or of the asperities. When the angles which characterize the asperities is low, a sort of cutting phenomena, as well as in tools, can happen. When instead this angle is higher, we have a sort of bluffing. But in any case, you see here we have wear tracks because materials is going to be removed from the soft material surfaces. Also, polymers can be subjected to this kind of damaging phenomena. We can experience adhesive wear in polymers, as well as we can experience abrasive wear. And what it happens is that the transition from one to the other phenomena, which has a reflection also on the wear coefficients, is usually dependent on the roughness of the surfaces. The adhesive wear, which is going to be present with very low surface roughness, can also result in a very reduced value of wear coefficient, and thus in friction coefficient, because, and that's the case, for example, of thermoplastic polymers, due to the stresses which are present at the contact, we can have a sort of alignment of the macromolecules of the polymers itself, and they tend to reduce in this way, let me say, the interaction points among the two surfaces, and thus reducing the wear rates. The third case of wear is that which is called erosion wear, which is a little bit different from the two previous ones, because in this case we do not have two solid bodies sliding one with respect to the other one, but we do have particles which are transported by fluid, which could be in general solid or, liquid or gas phase. The most cases we are talking about liquid transporting solid particles, which impact on the surface of the materials, and then they cause materials consumption, and that is wear due to erosion. For this kind of tribological problem, we do have many parameters which are going to control the severity of the erosion wear. First of all, it is different if the materials, the base materials which come in contact with these solid particles is a ductile or a brittle material. So the severity depends on the properties of the base materials itself. Then for what it concerns, let me say, the particles, what is very important is, one, the angle of incidence here, the mass and shape, that is shape and size, given obviously the properties of the particles itself, of the particles impinging on the materials which will be consumed, as well as the velocity of the particles itself, which are transferred, for example, by the fluid transporting the particles. First of all, what is going to happen in terms of difference between ductile and brittle materials? If we have a look to the qualitatively to the erosion rate, that is, in this case, the volume of materials which is consumed per unit time. We do not refer to unit of sliding length, because here there is no sliding. We see that if we have a brittle material, that is a material with low capacity to absorb energy by impact, low values of fracture toughness, if we increase the angle of incidence from 0 to the maximum value, that is 90 degrees, so 0 should be this one and 90 degrees should be this one, we see that starting from 0 in terms of erosion rate, at 0 value of the angle of incidence, we have a maximum when we reach 90 degrees as the angle of incidence. And this can be explained quite easily, because if we have our particle which is moving in this direction, that is with a velocity vector which has two components, a normal component and a tangential component with respect to the surface, obviously the tangential part of velocity does not give any effects on materials consumption. What is going to give effects of material consumption by impact and related phenomena is the normal component of the velocity. So the kinetic energy is very important, and is very important the kinetic energy which is referred to the normal component of the velocity of the single particles. Thus, if we are going to move from 0 to 90 degrees, the normal part of the kinetic energy is the maximum, and this can explain to us why we can expect an increasing erosion rate. What is a little bit strange, but it can be explained, is what is happening instead if our materials is a ductile materials, that is, it can show plasticity effect. You see here that if we increase the angle of incidence till values which are around 20 degrees, we have, for the same reasons we have explained before for the brittle material, an increase in erosion rate. But after this, the erosion rate is going to diminish, reaching, let me say, the minimum value, if we exclude the zero value of the angle of incidence, when we have 90 degree in terms of angle of incidence. And why this can happen? Because if we are going to, let me say, put our particles with a high velocity just in a normal direction, and this is a ductile materials, what it can happen is that these having, for example, very sharp point, a very specific shape, this particle can be embedded inside the materials itself, and so there is no reduction in material consumption due to the fact that this base material is ductile, so it can be plasticized, and the particles can then be embedded. Just to figures this kind of phenomena, think, for example, in the case in which you impact hard particles on butter. So these hard particles on butter is embedded, remains entrapped in a, let me say, a more probabilistic way when the angle of incidence is 90 degrees. So if we have a look on the angle of incidence and we would like to act on these parameters in order to reduce the erosion rate, if we have brittle materials, according to the angle of incidence, we just need to reduce the angle of incidence. If we have ductile materials, we can move through low value of angle of incidence or also to very high value of angle of incidence. This can be accepted or not. That depends on the application we have in mind, because in the case we are going to use positively this effect at 90 degrees, what is going to happen is that the particles are embedded on the surface inside the material. So we are changing the surface materials compositions, and we are changing, generally speaking, surface materials chemical physical properties. And so we must ask ourselves if these changes can be accepted for the special function, for the function to which our component has been designed. We can make some modeling about erosion, starting from the kinetic energy related to the angle of incidence. What is going to happen is that in this field, in this area, let me say a very simple equation as those of our card that we have defined for abrasive, for adhesive wear, are not essentially working. And so we move through semi-empirical equationship, like, for example, this one, which is typical for a normal incidence, in which all the most important parameters which can affect the erosion rate, E capital letter, are reported, and from which we can have, let me say, some guidelines in order to understand how to reduce erosion wear, provided that we cannot remove particles inside the fluid, because if we can remove particles inside the fluid, obviously this phenomena can be cancelled. And there is one difference important that we now will discuss with respect to adhesion and erosion wear in the case in abrasive wear in the case of erosion wear. But let's go in order. You see here that we do have, apart the values of the exponent, we do have the erosion rate, which is related to the curvature radius of the single particles, because if we do have particles sharp like this or particle like this with a blunted profile, obviously this means that the area onto which the kinetic energy is dissipated is very low in this case, is more higher in this case, and thus also the induced stresses are are lower in this case. So if we reduce the radius of curvature, we need to have the potential increase in erosion resistance. Then we do have properties, obviously, of the particles in terms of hardness, as you see here, by the exponent. We do have here the velocity multiplied by the mass density, that is a parameter which is related to the kinetic energy which is dissipated upon impact. And we do have also another important parameter that we know, which is not present in adhesive or abrasive wear, which is the fracture surface of the substrate, that is the fracture surface of the materials which can be consumed. Because what is going to happen is that this very, let me say, impact, this impact due to the particles which are going to impinge on the transported by the fluid on the surface of our component, they are going to transfer depending on the incident angle energy in a kinetic energy in a very short time. So here we do have high stresses, and these high stresses can cause the formation of cracks and thus also the material removal. And we know that the crack formation and crack propagation are related to the fracture, let me say, resistance properties of the surface. So we cannot be surprised if, having in mind the value of fracture toughness, this value of fracture toughness is inversely proportional to the erosion rate. That means if we increase the fracture toughness of the surface, we also reduce the erosion rate of the surface itself. So also fracture toughness is an important parameter which is going to appear in erosion, but is not going to appear for what it concerns adhesive or abrasive wear. And thus, if we want to, again, also polymers can be subjected to erosion phenomena. What is going to happen for the, let me say, three basic classes, that is polymers behaving as glassy polymers, that means thermoset materials or thermoplastic materials at a temperature value under the glass transition temperature, or polymers behaving as ductile materials, that means thermoplastic materials at temperature higher than the glass transition temperature, or the other class, that is the mixed way, the elastomer. What is going to happen is that the elastomer, generally speaking, they have a low erosion rate because due to the high elasticity behavior of elastomers, particles are bounced off. In terms of ductile, we can have polymers, we can have a high erosion rate in the form of ductile erosion. For glassy polymers, that is brittle polymers, we do have brittle erosion that is higher, the highest erosion rate. Increasing the impact speed, it gives a strong dependence for polymers on the increase of the erosion rate, as well as also, but with less degree of dependence, the increase in particle size. If we increase the temperature, and we have materials, polymers, which are sensitive to temperature, we can have a decrease in the erosion because we can have a transition, for example, from a glassy behavior to a ductile behavior. In the case, we do have thermoplastic materials that show, as mentioned before, a glass transition temperature. Thus, what can we do to reduce wear? Depending on the type of phenomena, which is let me say, the basic phenomena of material damage, we have, as we have said before, different possibilities for abrasive wear and for adhesive wear. When we want to reduce erosion wear, we also can use the possibility to coat our material with a harder material in order to increase the substrate hardness. But we need to keep in mind, and so we give to the final conclusion, even because there is another concept that we need to keep in mind, that for as we have seen, for erosion, we have also the fracture toughness, which is very important. And that's the first case. The second case is that generally speaking, we could have the possibility to consider at least a couple of these phenomena together. For example, erosion where coupled with adhesive wear or coupled with abrasive wear, think the case the particles still remains, let me say, entrapped to some extent. And so generally, when we are talking about wear resistance coatings in which we need to obtain a good resistance to at least a couple of these potential damaging mechanisms, we want to increase the hardness of the surface, first of all. We want to increase erosion weight, the fracture toughness of the surface to be protected. And these two properties, as we know, they are not going together. I mean, if we have a material, general material, and we increase the hardness of the materials, we usually reduce the fracture toughness of the materials. So for these reasons, you will meet in many applications the solution to reduce tribology problems, to reduce wear, abrasive, adhesive, or erosion-based wear, by referring to CERMET materials, a class of materials that we have already discussed when we were speaking about surface engineering methods. That is, materials which have a metallic phase and which have also a ceramic phase. One important we have mentioned for to be applied, for example, with HVOF, that is with high velocity oxygen fuel spraying-based technology, if you remember, was tungsten carbide cobalt, for example. This is a CERMET. This is a CERMET which is able to give to us a compromise between these two requirements, because the use of the ceramic phase is able to give an increase in the hardness of the coatings. And at the same time, the presence of a metallic phase is going, let's say in this way, to reduce problem of reduction of fracture toughness, because this allows to us, with respect to a full ceramic coating, so to have an increase in fracture toughness of the materials, and in this case of the coatings, and in this case of the surface. And so this solution that we have seen, for example, in landing gears, is one of the most common solutions when we want to reduce the severity of wear problems, because it is able to give to us benefits, even though we need to think to erosion wear, or we need to think to abrasive wear, or we need to think to adhesive wear. Also for adhesive wear, that this gives to us benefits, the CERMET solution, because the presence of the ceramic phase, which is not a metallic phase, having said before that adhesive wear essentially is going to happen for metallic alloys, the presence of the ceramic phase is able to reduce the metallic behavior of the surface, so is able to reduce the possibility to have the formation of micro weldings, and so it's able to reduce the severity of the adhesive wear. So As you have seen, we have left at the end of our lectures the topic of surface engineering technologies, corrosion and wear, because they are strictly related. And most of time, apart from the solution that now we should know very well, having talked about that many times, of coatings in terms of thermal barrier coatings for gas combustion chamber, for turbine blades, for example. The solution to overcome corrosion problems or to overcome tribological problems, let me say a standard temperature, not high temperature as in engines, needs to be considered together at the same time, because we can have both the phenomena, and we can have these phenomena which are able to be synergic, and so must be studied and must be defined solutions which are able to reduce the severity of both, thus increasing the lifetime, the expected lifetime of our components. Another important thing that you should remember in this case is that when we use surface engineering methods, and we are talking about, let me say, about surface engineering, so with an engineering approach, we are not asking to modify the surface of our components in order to have an infinite lifetime. What we need to achieve is that the expected lifetime is able to match the lifetime at the design stage. And thus, this means that we must, let me say, make optimization between cost, between selected technology. And as engineer, what is important for us is that if the component must work for 5 years, I just give to you an example, well, we will look and select a solution in terms of surface engineering technology, which is able to guarantee to us 5 years of lifetime, not 10, not 15, not 20, because that would be not an optimized solution. With this, I'm going to come back to my face. We have finished our course of aerospace materials. As you have seen, all the examination are open on the InfoStud. There are still already reservations for the next examinations, and to all students which have been booked, I have fixed for this 4th section 2 days. They have received an email by InfoSud system. The first is Friday, 4th of June, and the second date is Monday, 7th of June. So the interested people have already received the link to be connected with me, because for June, and I guess also for July, but you will be promptly advised, the examination will not be in presence, but will be in a remote mode. And so for each section, you will receive from myself, exclusively through InfoStud, the calendar, which must be considered in order to make that examination. There is another question which somebody of you made to me by mail, asking to what topics must be prepared for the examination. It would be quite simple. I mean, my answer is quite obvious. All the topics that we have discussed, and all the topics that you have on your Google Drive, on which you have all the materials that they have been discussed during our meetings. There will be no written examination. There will be only an oral examination. on that topics with no preferences. I mean, any topics of those we have discussed can be asked to you for the exams. That's all for me for today. So I would like to know if somebody has some questions.
Prof, io ho una domanda. Quindi di carattere legata agli esami. Quindi da quello che ho capito sarà lei a fornirci anche nel caso di luglio le date che decide di fissare.
Sì, assolutamente sì, nel senso che questo dipende poi anche dalla numerosità dei prenotati, no? Ovviamente. Le date, adesso poi lo dico anche in inglese, le date in cui l'appello è aperto su InfoStud non coincidono con la data in cui si fa la prova.
Sì.
Chiaro? Per
sì,
cui
questo sì, certo.
è la finestra che si apre, dopodiché
certo.
Io vi manderò sempre via InfoSud i giorni in cui ci sono gli esami e anche il collegamento in remoto, fermo restando il fatto che, e lo dico per voi, lo dico solo in italiano perché i colleghi stranieri probabilmente non sono in questa condizione, che se qualcuno ha piacere di venire a fare l'esame in presenza certamente lo può fare, me lo dice e troveremo il modo di farlo. Però organizzare in questo momento esami orali in presenza, in considerazione che molti corsi fanno la prova scritta, diventa un pochino complicata e la delibera della facoltà dopo le prove scritte, insomma. Però ribadisco che se qualcuno vuole fare l'esame in presenza, per me va più che bene. Okay.
Sì, no, gliel'ho chiesto semplicemente perché per esempio con altri corsi dove però siamo anche molti meno, il professore in cui avevamo anche lì solo orale aveva detto ragazzi se voi volete poi essendo pochi organizzarvi in una data che preferite, però capisco che qua è
No, Francesco, vi dico anche un altro, io ho sempre fatto così, anche in questo corso, solo che in questo momento, data la numerosità, mi resta un po' complicato per il fatto che dobbiamo lavorare in remoto, solo per quello. Non appena finisce questa benedetta rottura di scatole della pandemia, sarà sicuramente ripristinato quello che ho fatto in tutti gli anni precedenti, cioè ho dato ai ragazzi la possibilità nell'ambito della finestra di mettersi d'accordo, di scegliere una o due date con l'unica cortesia di chiedere un'aggregazione, come dire, significativa.
Certo.
Però adesso mi resta un po' difficile anche per il fatto che ho in contemporanea gli esami del corso di base, dove invece c'è lo scritto, quindi è un po' un macello da questo punto di vista.
Ho capito.
Per quest'anno dobbiamo procedere in questo modo. Poi è evidente che se nei giorni in cui ho fissato l'esame ci dovesse essere qualche problema, vabbè, insomma, ci sentiamo, troviamo una soluzione.
Certo, va bene, grazie.
Ok, any other question? Okay, it seems to me no question. So, dear students, I greet you and we will meet again when you will decide to make our examination. Good afternoon to everybody. Arrivederci a tutti, ci vediamo agli esami. Arrivederci.
Arrivederci, prof.
Grazie, professore.
Arrivederci.
Ragazzi, scusate se avete necessità di